All right, exercise 13C. So remember, chapter 13 only has 4 exercises, 13A, B, C, D. A and B was revision of year 7 to year 11 probability. Year 11 mainly was conditional probability versus independence. Everything else, from Venn diagrams to tree diagrams to two-way tables to mutually exclusive, addition rule, multiplication rule, all of that was year 7 to 10. Okay? So the only part of year 11 was the conditional part, and understanding the difference between independence and conditional. Today, we're still going to use all of that knowledge, but we're introducing this concept of a distribution of a data. Your data can be in 2 particular types, and they normally call it discrete or continuous, and that's what separates the chapters. So chapter 13 and 14 are discrete, 15, 16 is continuous, and then 17 is a merge of the 2. Okay? So let's fill in a couple of blanks here. A random variable has a value determined by the outcomes of an experiment. So when you do a trial or you're testing something, you are doing an experiment, and the result of that experiment is the random variable because you don't know what you're going to get. Okay, it's like rolling a dice. Random variables are expressed as uppercase letters. Okay, so we usually use a capital X to represent the random variable, and then the values that it can possibly take, we take it with a lowercase. What do I mean by that? So here's an example. If you roll a 6-sided dice 5 times, okay, so if I roll it once, I roll it twice, I roll it 3, 4, and 5, the possible outcomes I can get, okay, so there are 6 options there. But if I say let capital X, which is the random variable, be the number of times a 3 comes up, then the scenario comes as this. I either get a 3 on the first go, or I might not, but I can get a 3, not a 3, 3, 3, and then not a 3. That could be one possible combination. This is how many 3s did I get in this scenario? I got 1, 2, not that one, the other one, 3. So that means my random variable X, which remember means to get number of times I can get a 3. Number of times I can get a 3, right? So in this particular outcome, in this particular trial, in this experiment of rolling a dice 5 times, I got capital X equals to 3. The confusing part for a lot of students is the notation is, I might say, what's the chances then? So what's the chances of getting 3? Now that one doesn't look confusing. It's this one. But it means exactly the same. You can see how I guided you. So the idea was, I said if you rolled it 5 times, what's the chance of getting 3 3s? So you got 1, 2, 3. So this X is the capital X that represents all the random variables I'm interested in. So what's the possibility of getting a 3? That's what a capital X is. In this particular scenario, I'm looking at X, capital X, the random variable being having 3 3s. Yeah? Here, if I said, well, what's the chances of getting 3 3s if you roll the dice 5 times? This is what it's saying. Probability of getting the random variable X, which is chance of getting a 3, the 3 of them, right? Here, this notation, one is a capital X and one's a lowercase x. The lowercase x is used to represent the possible value or number of times I want it. Okay, so this one, that was capital X tells me what I'm looking for. This is how many times I'm looking for it. So that's the difference between the two. So if I started off there, a lot of students get confused. But if I go backwards, it makes a lot more sense. Yeah, so we're just saying that little 3 is that little x. So when you're looking at the notation in the textbook, if you're getting confused by something like that, that's all it's trying to say. So it's just saying that what are the possibilities of your little x? I can get, if I rolled it 5 times, I can get 0 3s, 1 3, 2 3s, 3 3s, 4 3s, 5 3s. Those are the possible little x's. This is the notation that you use. Capital X is the random variable, and little x is the possible outcomes. Does that make sense? Okay, so it's just reading notation there. So I find a lot of students get confused with that, what that actually means. It's just another way of saying, I want 3 3s, or I want 5 of whatever it is I'm looking for. All right, so now that we understand that notation, that's just talking about random variables, possible things that you're looking at. We talked about two types of data that you can end up getting. You can either get discrete or continuous, and for those who don't remember back in year 7 stats, discrete are things that you can count, so it's countable. Continuous, think of it as things that you can measure, so it's measurable. Okay, so your height, your weight, anything, time that has in-betweens, that's continuous because it can be anywhere in between. Whereas discrete, like your shoe size or your t-shirt size, can only be small, medium, large, or XL or XS, but it's stuck. It's discrete. It's countable. Yeah, you don't have anywhere in between. So we're going to be looking at Chapter 13 and Chapter 14 explores countable data. Chapter 15 and 16 explores continuous data. And then 17 merges the two. Okay? So discrete data can be countable. Just fill this one in. That's countable. Number of siblings, shoe size, postcodes, whereas continuous data can be measurable. Okay. Let's do an example so that we can tie in what we're doing in exercise 13C. 13C is getting you used to using the table I just showed you before with a notation. We're taking the data that we have and then we're going to draw a graph out of it. We call that a distribution. Okay? Here we go. Let's take this example. First one. Example 1. 2 coins are drawn from a bag. So you draw it from a bag containing 2 white and 3 black coins. All right? With replacement. So with replacement. So let's think about it. On your first go, in this bag, remember, I'll draw a bag. And the first, you can either get white or black coins. There are 2 white coins and there are 3 black coins. So how many coins are there in total in this bag? There are 5. So there are 5 coins in total. And we're saying that we're going to draw 2 coins from the bag. So draw number 1. My possibilities are I either get white or I get black on my first go, right? I don't know which one, but I do know the chances. What's the chances of getting white on my first go? That's right. 2 out of 5, 0.4. And then that means black is 3 out of 5, which is 0.6. Then I say, all right, well, that was the chance of getting my first draw, but remember it says replacement. So after I take it out, I still put it back in. So if I've taken a coin out, there's meant to be 4 left, but with replacement means I put it back in. So I should have 5 coins left over still. So therefore, in my next go, I can either get again white or black, depending on what my first go was. And the data is still the same. I still get 2 out of 5 for white. I still get 3 out of 5 for black. 2 out of 5, 3 out of 5. Great. Now we were to work out the chances now. So let's start using the language of random variables here. Let x, which is a random variable, represent the number of white coins. So I'm only interested in getting white coins. Okay? If we organize the table of outcomes, these are the possible outcomes. So capital X represents number of white coins. Yeah? So in my 2 goes, remember you could have got white and white or black first, then white, or black and black. So if I'm just interested in the white coins, okay, what's the possible outcomes? Meaning the little x. So when I say little x, what are the possibilities that I can get for white? What's the possible number of abilities? How many white coins can I get in 2 goes? What are the possible outcomes? What can I get? I'll start you off. I can get 0 white coins. That's one possibility, which is equivalent to black and black. So I can get black and black, which means 0 white coins. What's another one? You can have 1 white coin, which represents, you can either get 1 white, 1 black, or 1 black and then 1 white. That's what the number 1 represents. What's the next one? 2. Well, we just did 1. You can have 2. So if you have 2 white coins, Two white coins can represent right there. That's W and W. But the reason why there's four rows there is because I actually... Oh, I see why you said one again. I see what you mean. I actually split it up initially so that you can see the difference. So this is 1 and 1. Technically, when you do the table, you don't count it twice. But because I'm showing you the possible outcomes, then we'll write it as 2 there. Okay, so your outcomes are you either have 0 white coins, 1 white coin, 1 white coin, that scenario, and the last one you have... Oh, sorry, that's white. White is 2 white coins. So that means your capital X ends up being saying it could either end up with 0, 1, oh, sorry, I should have filled it over here. B, B, W, B, B, W, W, W. And I just realized I was meant to run it the other way around. All right. Now, let's calculate the probabilities. If I want to know the chances of X equals 0, meaning I want the chances of getting 0 whites. 0 whites is the same thing as saying getting a black on the first go and then black on the second go. So on your tree diagram, you're essentially asking, what's the chances of getting black? That was 3/5. And then you get black again, that's another 3/5. So if you have to calculate that, you're using multiplication rule. So you're calculating what is 3/5 of a chance of 3/5 of a chance. This is like 60%. So you got 60% to get a black on the first go, and then you got 60% chance of getting a black on the second go. So it's 60% of the 60%. That gives you 9 out of 25 chance of getting 0 white coins. What about 1? How do you calculate for 1? What do you do? Let's go with... We're already on this side. Let's go this side. Tara, how would you work out for the probability of getting 1 white coin? Very good. Tara realized that there is... Whoops, sorry, over here. This is 1 white coin scenario. So 2/5 times 3/5. And we also have another one where to get a white coin... 3/5 times 2/5 again, so hence you double it. Yeah, so we can say chances are 2 out of 5 times 3 out of 5. That's your getting a white first, then a black. But you also have getting a black, then getting a white. That's still 1 coin as well. So therefore, it's 3/5 getting a black times 2/5 getting a white. So together, that's the chances of you getting 1 white coin, which is really doubling 2 times 3 and 5 times 5. So that's what? 6/25 doubled is 12 out of 25. Okay. And then same thing with 2 white coins. So that just means 2 white coins is 2/5 times 2/5. It's up here. So 2/5 by 2/5 gives you 4 out of 25. What you're learning today and what you practice in 13C is literally that table that's right underneath that. Okay, not so much this. This is the theory so you can see it. You don't have to draw the tree diagram and all that. It's just that table. So that table is getting you used to understanding X. Little x represents the possible values that capital X can take. Capital X is getting white coins, but how many white coins can you get in 2 rolls or 2 flips or 2 draws? You can get 0 white coins, you can get 1 white coin, or you can get a maximum of 2 white coins. Okay, so the number of trials you do determines the number of X's you can observe. All right? We already worked out the probability. It was 9 out of 25 plus 12 out of 25 and then 4 out of 25. Now we know that the sum of all probabilities must add up to 1. So 9 plus 12, which we get 21, and then 21 plus 4 gives you 25 out of 25, which makes sense. If that table does not add up to 1, something is wrong. Okay, and that's where you got to go back and just double check. But that is what you're training to do in 13C. Training, because now it's about what we call discrete random variable distribution. It's about plotting that and visualizing. What does that look like? The more trials you do, what kind of pattern do you observe? That's what this is. Okay, so that's called a random variable distribution. Well, this case is discrete because the data you're working with is countable. How many whites do you get? You get 1, 2, 3. You don't get 2.2 of a white coin. You get exactly the value. Okay, so that's called discrete. All right, team. So let's go. What do we have? What do you now have is a discrete probability distribution function, meaning x-axis represents the random variable x, and the y-axis now represents the chances of getting it. Okay, this is you can actually now plot that and you get a distribution. We can use our CAS to draw this probability distribution. Remember, if it's a probability distribution, the graph has to satisfy two things. One, probability can only be between 0 and 1. So that means your y-axis has to be between 0 and 1. Okay? And the sum of all probabilities must add up to 1. Okay? So it has to satisfy those two. Now let's practice your CAS just so you know how to sketch this onto a CAS calculator if you want to look at the distribution. Let's do a quick one. Here we go. Open up your CAS. I'm just going to go to Home. Go to List in Spreadsheet from the front screen menu. You can label this little x PR for probability. Okay? So I just labeled that as x PR. Possible x's you can get, Noah, thank you. 0, 1, 2. So that's your x-axis values. It's the possible number of white coins you can get. You can get in two draws. So you get 0, 1, or 2. Probability of 0, we said it was 9 out of 25. What was 1 again? It was 12 out of 25 and then 4 out of 25. To then visualize this, you add on a page, Control Doc, and add on data and statistics. So you can go back and forth, yeah, like that. Remember, x-axis is meant to represent the random variable. Well, in this case, it's discrete. So random variable x, so that's my x-axis there. And my y-axis is meant to represent PR, which I labeled before, is the probability. And there's my distribution. Obviously, the more data you have, then you can see a better distribution. And then you can describe the distribution later on. So when we do binomial, you can then see how the graph looks. And you can test what happens when you increase n, what happens when you change the mean, what kind of graph are you expecting. That's essentially what they want you to understand. Okay, so it's a function of the probability distribution, but to put it into the probability distribution, you just have to understand how to use the variable x, okay, random variable x. Coolies? There you go. Let's go back here. So let's now put to the test on our understanding. Flip over the page, and this is our last page over here. So let's have a look. Example 2, which of these is a discrete probability function? Give reasons why or why not. Have a look. I'm going to give you 2 minutes to have a think. It's 9:28. So by 9:30, you should have a response for example 2. What are some things to look out for? Is this a discrete probability? 2 minutes. Let's go. State with reasons whether the following is a probability function or not. So